Great. Can you guys all hear me okay? Okay, great. Cool, thanks for having me. This is a beautiful space. It's a beautiful day today. And today's talk is gonna be on building and instrumenting knowledge assistants. For those of you who don't know me, I'm Jerry, co-founder, CEO of LlamaIndex. It's a startup building a developer platform and framework enabling developers to build LLM applications over their data. So let's get started. We've talked a little bit about this in the past few months, but for the past year or so, or especially last year, there was a lot of emphasis on this idea of RAG. And RAG really is just a technique to get to this overall use case of building a knowledge assistant. A knowledge assistant is really, for any user that or any company that's interested in deploying this throughout the enterprise, you want to build an interface that can take in any task as input and get back an output over your data. Oftentimes, this is both for internal use cases as well as external. Internal use cases including a chatbot for your end user, like the sales team or finance team. End user use case, like a customer support bot. And so the input forms to this knowledge assistant can either be very simple questions, or they can be very complex questions, or actually just very vague, long-running research tasks. And the output forms could just be like a short answer, like a simple response. But if you think about this in its general form, it could be a lot more complex than that. It could be like some sort of structured output. It could be like an entire research report. So you generate multiple pages of something to like an entire report that you then give to your stakeholders. And so one of our takes is that last year was a year of everyone trying to build a demo of RAG, and this year everyone's trying to build agents, and RAG really is just the beginning, right? RAG was just an initial technique towards building a production-grade knowledge assistant. A knowledge assistant with basic RAG has the following pitfalls. One, you actually try to build this sort of chatbot or QA interface over your data, and then you employ the most naive RAG techniques you find on a YouTube tutorial. You will probably do something like the following. You take in some sort of data, you figure out a way to do some sort of paragraph or sentence splitting, and then you embed each chunk and you put it into a vector database. During the query side, you are going to do some sort of dense retrieval from that vector database, set your top K to some value, and then take that retrieve context and put it in a QA prompt. There's a lot of issues. One is the data processing piece is a little bit naive. You're probably using an off-the-shelf parser. You're just doing splitting without really thinking about the implications. The retrieval side is also basic. You could probably do some better retrieval. And then the LLM call is just like a one-shot LLM call at the end. So it's really not tapping into the capabilities of these language models that have very powerful emergent reasoning capabilities and not just synthesis capabilities. So we think that RAG, in its naive state, is a little boring. And the use cases it unlocks is also boring. You get limited value add from just a glorified search system over your data. It doesn't really automate decision-making that much, and oftentimes it doesn't really work. So one of our thoughts is, can we go beyond simple search and QA to building a general context-augmented research assistant? There's three main parts to this towards building a better knowledge assistant. The first is, before you think about all the fancy agent stuff that you see out there, just having really good data processing and retrieval modules. Having that as a core building block before you tackle the other ones is a good recipe to basically make sure that your data interfaces and your data quality itself are good, which minimizes hallucinations down the road. The second piece here is single agent query flows, or just layering on agentic layers on top of a standard QA RAG interface with basic retrieval to basically add on some degree of query understanding, sophistication, and also add state over time. The third is, as you actually generalize beyond just a single agent into thinking about a multi-agent setting, more and more people are actually building just these general multi-agent task solvers where each agent can specialize in a certain task, but collectively achieve an outcome at the end. Let's start with advanced data and retrieval. To some extent, this is like our bread and butter ever since we started as a framework and generalized into an enterprise platform. Garbage in, garbage out, right? I think we've all heard that term in the context of ML, and it's also true in the event or in the case of LLM applications. In ML, this term usually applies to stuff like, data preparation, like, figuring out how to impute missing values, like feature engineering, that type of stuff, especially if you're trying to like train a model. In the LLM use case, because you're not training the LLM typically, you're trying to orchestrate an application around it. The context is like you need a good data processing layer so that if you're trying to import data from some like unstructured files, be able to make sure that data is in good quality before you feed it to the rest of your application. Some of the main parts of data processing include document parsing, document chunking, and then document indexing. So these three should be all pretty familiar to anyone who's like built a RAG pipeline. And what it really constitutes is like a new type of like data stack. It's like a new type of data ETL that translates like unstructured data into some form that the LLM can actually like crunch through and understand. And I just outlined what a naive stack would be. And so maybe I'll take you through a little bit about what some of the more advanced components would look like. The first piece is parsing. So if you use an off-the-shelf parser, oftentimes within a lot of companies, you have these documents that don't just have text, but also a lot of images, tables, and diagrams. And if you just use an off-the-shelf text parser, it's going to, one, probably like collapse that information, two, like not parse out some stuff that's like in your like images or diagrams. And for tables, it might rearrange it the wrong way. And oftentimes we found that no matter how good the downstream LLM is, like we've tested with like the state-of-the-art LLMs out there, they're not very good at like piecing together information if that information has been jumbled to begin with. So oftentimes if you have like a document or a PDF with like tables, and that table's like super jumbled, you ask a question over those tables, you get back hallucinated answers. And before you even think about like indexing, retrieval, or agents, good parsing itself can be a strong baseline to improve performance. What we did was we took the Caltrain schedule. There's a lot of other examples in that repository as well. Plenty, like including like financial reports, like insurance documents, healthcare, and we took this table and we parsed it using, we built this parser called LlamaParse, which is specifically designed to help you parse out like complex tables. When you actually lay it out spatially like this, so that it's all like kind of nice and that the columns are all consistent, it turns out the LLMs actually understand this pretty well too. So we haven't even parsed this into like Markdown, or you're not turning this into a pandas data frame. You're literally just like formatting text and making sure it's laid out the right way. And when you do that, LLMs have a pretty good time actually making sure that you're like, if you ask a question over this table, that's consistent with that it's like pulling in the right values from the right place. So compared to like a naive parsing approach, when we ask a question over the stop times for a given train, you get back like the right answer when you have good parsing on this data compared to bad parsing. Beyond just the parsing piece, you can also do a variety of things that go way beyond just standard chunking and vector indexing to basically create a more advanced index/retrieval flow over your data. And this is actually relevant, especially once you get into the age of, or like the era of like building more multimodal applications. One general thought is you can combine parsing with not just like flat chunking and indexing, but some sort of like hierarchical indexing retrieval to model like heterogeneous data within the document. To take a look at what I mean by this is, let's say you split like a complex document into the constituent parts, so like a table, a text chunk, and an image. For each element, like let's say this is an entire page of a document, this is just like a 2D table, and this is an image. You don't necessarily just want to embed that object directly, and also for images, unless you use like a multimodal image embedding, you can't really. So a good technique that we found is extracting like multiple representations of the same underlying object. So for like a big page, extract out a bunch of like representations of that page For a table, extract out like the summary, or also extract out every row as its own representation. For an image, extract out like captions or some sort of like structured annotations. And then these like nodes, which are typically text, you put those into a vector store, but they reference the underlying object. And so this is what we mean by imposing like a little bit of like a hierarchy to this process, because you're separating the representation you use for retrieval versus the one you use for synthesis. We typically found that this leads to better results, and this is made possible by just some of our enterprise offerings. So we are working on Llama Cloud, which is an enterprise offering that complements the open source framework. It contains basically the core components you need for advanced unstructured data processing for LLMs. So this includes like the advanced document parsing you see that can handle like tables, charts, and images, and also some of the advanced like ETL techniques like the hierarchical indexing, processing, and retrieval. So there's a wait list open if you're interested in signing up. But after that, let's talk about single agent flows. So okay, you got the data piece down. You've set up some sort of infrastructure on your data side to make sure that your data is high quality and you have a good retrieval interface over that. Afterwards, let's think about how to build some sort of like agentic components that make your QA system more sophisticated as a knowledge assistant. And this is one of the parts where like Arize Phoenix or LlamaTrace actually comes in. But there's an entire spectrum of components from the core building blocks that make up an agent to entire agent systems. And they all come with trade-offs in terms of like capability and expressivity, but also reliability. So full agent systems, like a function calling loop, like the OpenAI Assistance API, this stuff is going to get better and better over time. They contain like not just query planning, but also tool use, like memory, basically a bunch of these components into like a class that you can just use off the block or out of the shelf, off the shelf. And the issue, I think, is that they typically incur higher token costs, higher latency, which will go down over time, of course, but also sometimes a decrease in reliability. Oftentimes, what we see in people building agentic flows in production today are actually just like maybe leveraging some core building blocks like tool use or memory, but really imposing a lot of like human constraints in this process. And this leads to stuff that's like systems are a bit more predictable in nature, but obviously it's going to be less dynamic and expressive because you're the one defining the constraints as opposed to letting an LLM figure it all out. We think about agents as like basically layers you can build on top of a RAG system, and this overall concept, we coined the term Agentic RAG. So we have like a deep learning course with Andrew Ng on this as well. But we basically treat every data interface as a tool. So a vector database, instead of just passing the query directly to the vector database, you can treat it as like a function that you can call to basically infer the parameters of that interface. There's also other tools like structured data. There's also like general API interfaces you can get the LLM to interact with. And an agent is some sort of like compute layer on top of this that can leverage a few building blocks. So tool use, learning how to actually infer the parameters of a tool. Having a query planning layer, by default, it's just like chain of thought, next step prediction. You can go a lot more complex than this. You can plan out like a DAG, a tree to tackle like complex tasks. And you can also input other components like reflection and memory. So towards building generally, like if we think about some of the pieces that make like a single agent more reliable, one is we see more and more people not just using off-the-shelf like a React agent, for instance, or an agent that just like calls function calling in a while loop. We see a lot of like custom implementations of agents. And so to that end, it's important to be able to create some sort of like core abstractions to let users basically just like define whatever agentic reasoning you want with some aspect of like guardrails, being able to impose explicit like constraints on how that agent can behave and what tools it has access to. Other pieces of being able to develop an agent include control, so actually being able to guide the intermediate steps of an agent step by step. We're currently working on some like cool projects that are basically like completely open source to enable you to better like debug and play around with the intermediate states of an agent's execution. More on that soon, probably in like a month or two. And then, of course, observability, tracing, and evals. There's a lot of great tools out there for observability tracing, and the overall idea is that you're able to actually really deep dive into every step of the agent execution process, see what's going on, and be able to evaluate any subset of that execution. And so that's where we're excited to partner with Arize on the Phoenix product, which we've integrated a lot in the past few months on the open source local version. But specifically now, we're excited to kind of integrate with them on their hosted platform. And we're coining this term, this joint collaboration, as LlamaTrace, right? And I think a few characteristics of LlamaTrace basically include deep instrumentation that actually uses natively, for those of you who are kind of somewhat familiar with LlamaIndex abstractions, it uses our new instrumentation module that's more like the logger module in Python, as opposed to kind of an off-the-shelf like a callback system that you might see in other frameworks. What this means is you get way more detailed traces through literally every step of the execution process. And you can basically take any span throughout this execution and add it to a data set that you can basically later run evaluations on. So huge props to the Arize team for helping to work on this, and also props to some of our founding engineers who helped build and play around with this integration. So with that said, I figured I'd show a notebook on, or just a quick demo on how this works. And so here, we are going to show you how to basically instrument Llama Cloud agent. So Llama Cloud, right, just is our enterprise platform for helping you build and set up data indexes. And so to that end, we downloaded 10 annual reports from Apple, reports from Tesla, and we're just going to build a simple financial analyst agent. The only thing you really have to do to set up LlamaTrace is you do the following. You pip install a single package, which represents the integration that we have with Arize Phoenix. And then you just put down your API key. You can sign up for an account, get an API key, and call basically a single line of LlamaIndex code. You just call set global handler, Arize Phoenix, and call the endpoint, which is the hosted version. And OK, I'm going to zoom in a little bit, right? You specify the endpoint, and you're basically good to go. You basically don't need to worry about this anymore as you're writing the rest of your application. The next step is just loading the documents into Llama Cloud. Let me just make sure I have the right tab pulled up 1 sec before I switch tabs. OK. All right, going to show you this really quick. OK. So this is the overall interface of Llama Cloud. You can see that for a given project, you can basically have a central view of all the data pipelines that you and your team are using. So this is what we call indexes. And here, we defined an index where we uploaded all the files, Apple and Tesla, and it integrates with some sort of downstream storage system that you're using, right? And we handle stuff like incremental syncing, the processing, all the parsing, chunking, all that stuff. So we handle that in Llama Cloud, and then we switch back, and what you basically get is an endpoint that you can plug back into your retrieval code. So we took that code and we copy and pasted it here, right? And then you can basically just get back, in 1 line of code. OK, well, that's cool. Yeah, whatever. Basically, you can get back a piece of code that you can then build a RAG pipeline over. And so if you ask a question, what are the risk factors for Tesla in 2022, you can get back a response. And if I switch here, because I already preloaded this, you can take a look at the LlamaTrace interface, right? So this is the Phoenix interface that many of you might be familiar with. But one, it's hosted, right? So it's not just a local instance. You can basically access it anywhere. And you take a look at this trace, and you can see it is quite detailed. this is the simple RAG pipeline, right? It just does like retrieval and it also does synthesis. But you really get to walk through literally every single function in LlamaIndex that's being called to basically make this happen. And so we start off with the high-level query function. And you can see there's two main subcomponents. There's retrieval, and then there's synthesis. So during retrieval, I think what's kind of nice about Phoenix is there's actually an out-of-the-box like interface for you to view like retrieve chunks, right? So there's actually like a native interface to view like retrieve documents. It's formatted as well. And you can also view like the metadata on each document. There's also like the synthesis piece, which is our response synthesis module. And the most basic implementation is you just shove a bunch of text into an LLM. But we also handle for the fact that if you have like too much context, it actually incrementally goes through all the context, hierarchically summarizes it, and compacts it into the LLM. And so this is where you see all the steps of the response synthesizer running, where we actually run what we call compact and refine, or iteratively going through all the context, running a text splitter to split out the text, refining, and then also finally looking at the LLM call. And so this LLM call supports both viewing like the chat message interface as well as like a default completion interface. And you can see like the template that's being used, or sorry, here's like the LLM call. You see the system prompt, the user message, and then also any sort of like assistant prompt as well. So it's really detailed, and this is just like the basic RAG pipeline. When I'm about to show you like the agent execution, hopefully it works, then it actually gets like very interesting. So let's go into that. What we've done is here, we took a RAG pipeline, and in the spirit of like Agentic RAG, added on like a function calling agent on top of this RAG pipeline. This is just like a one line of code for simplicity, but it contains all the components of that agent. It contains like query planning, it contains memory, it also contains tool use. And we treated this RAG pipeline over this existing index as a tool that this pipeline can interact with. And we just asked the question, get property, plant, and equipment assets, which is one of these like numbers you have in your one of the tables for both Tesla and Apple in 2022. This is a multi-part question, and so we can rely on the query understanding layer in the agent to actually take this question, break it down into sub-questions. So Tesla property, plant, and equipment, and Apple property, plant, and equipment. We go back into the Phoenix interface, and we see there's a new trace being logged, which should be this one right here. Okay, and this is the one that I just ran. And you go into here, and it contains a very detailed trace of every single step that's happening in the agent. And you can make use of the horizontal scroll to really kind of look at every event and span that's happening, right? There's two main tool calls happening because there's the query understanding layer breaks down that question into two sub-questions. And then for each one, you can see the args being passed to the underlying tool. So this one is like Tesla. You go down here. This one is Apple. And each one, you can basically see that original like RAG pipeline trace being run, right? You see the retrieval piece. You have the retrieve and also the synthesize piece. So yeah, check it out. I mean, I figured I'd just showcase this as a demo, but I think it really does capture a lot of the stuff that we've put a lot of work in terms of like the LlamaIndex abstractions. Basically gives you a really nice surrounding tool for experimentation. And I showed mostly the tracing, but there's a lot of capabilities around evaluation as well. In the last few minutes, I just talk about the forward-looking stuff, like what we're currently hard at work on, which is we have agent abstractions in LlamaIndex. Obviously, there's a lot of interesting stuff out there around just like how do you build a proper multi-agent system. There's a lot of great frameworks, right, like AutoGen, CrewAI, and like LangGraph. But a single agent can't solve like an infinite set of tasks. And on one level, you can try to reduce this as like one agent or LLM tries to operate over like 10,000 tools and figures out just like everything that needs to be done to solve your task. But people are increasingly starting to create like multi-agent systems where every agent's a little bit more focused in scope, but they're able to communicate with each other to achieve a certain outcome. And so we've become very interested in this idea of multi-agents recently. And we see a lot of developers composing different levels of multi-agent systems. On some level, it makes sense because a multi-agent system lets every agent have a smaller set of tools it needs to deal with, lets them specialize in a certain task. You can give it a system prompt, right, so that that agent is very good at that specific task. But there's also systems level benefits. Like you can have, for instance, like 5 agents working at the same time, like in parallel to basically help solve this overall task, like MapReduce style. And some of the challenges in building multi-agent systems, just from kind of taking a look at patterns that people are building, is generally people don't trust these agents to just like free-form interact with each other completely. This oftentimes leads to just like stuff that goes off the rails. I think AutoGPT, for instance, was one of the first examples of this from last year. I mean, it was a great project, great like kind of showcase of what LLMs could potentially do. But just the current capabilities of LLMs didn't quite match up to the expectations. On the other hand, you have basically what is like a state machine or some sort of like graph style. You just like explicitly define the actual flows of how an agent can progress. And I think one of the challenges there is making sure that you as a human can actually know how to like define these flows and write the right code to define it, right? And so what we thought is we surveyed the landscape. And what we wanted to do is basically create a framework or an overall like kind of toolkit to enable people to actually model agents as microservices, right? And so that's where Llama agents came in. We announced this a few weeks ago at the AI Engineer World Fair. And the idea was to really leverage some of existing like principles around like kind of how software engineers like deploy infrastructure and set up like backend services, and make agents more production ready and robust. So what we do is we model every agent as a separate service. They can communicate with each other via some sort of like API interface and underlying message queue. And this allows you to basically set up a bunch of different agent services, reuse them across different tasks, and handle stuff like like batch requests and also streaming. So it's something that like is in alpha mode right now. We're still working on it, but there's a lot of existing cool kind of like contributions and interest already. We're currently working on some cool ways to basically like define very custom workflows while still letting you have this like high-level interface of having agents interact with each other. And so this is something that we're hoping to make a lot of progress on in the next few months. But basically, you have, for instance, just like a set of services, and you can watch them interact with each other to basically hope you solve this overall idea of building a knowledge assistant. So with that said, I think that's basically it in terms of my talk, and thank you.
Awesome. Amazing job, Jerry. Usually we like to keep these pretty interactive, so I think I'm going to do one question just based off time. So first hand that comes up. All right.
Thanks for the talk. Quick question on the example that you were showing about the simple RAG one. What sort of document level metadata or maybe like paragraph level metadata was being captured for a faster retrieval? Like certain times for these financial reports, certain sections appear on certain pages and whatnot. So like if there is anything of that sort.
Yeah, it's a good question. I think we find a lot of metadata extraction tends to be very custom and specific to the use case. I think some common forms of metadata that we see that are relatively effective include like just general tags that conform to a schema. So if you have a set of like topics, like being able to label it with respect to given topics. Page numbers and section headings tend to help as well, especially in terms of like retrieval and synthesis. And then the other piece, I think maybe the last piece, which I think is interesting for metadata, is taking in a chunk and then having the LLM during the pre-processing stage extract out like a set of questions for that chunk. So it's almost like if you're familiar with like Hide, it goes from like questions to hallucinated answer. Here you're like trying to hallucinate a set of questions that could be asked over this chunk. And we sometimes find that leads to like better retrieval, so that LLM can actually better understand what's going on, right? With respect to, like when you feed this entire chunk in, it's not just the chunk, but also, it's like, I know this chunk, like we can ask these types of questions over and get back the answer.